Yeah, so we are talking about GMC filter. By the way, before GMC filter, we studied band gap reference, comparator, and what else? Switch cap and GMC filters. So if you have some Butterworth or Chebyshev or any approximation based filter transfer function is available to you for a given transfer function, you can draw the schematic diagram, right? And from this schematic diagram, wherever GM blocks are there, you can replace them with some OTA, which you have already studied, right? So these are the tasks you need to do. And this one you designed it, right? Band gap reference and LDO. Yes or no? Okay. Comparator, you designed it. Okay. Something was switch cap circuit I gave you or no? So right now no assignment has been given on GMC filter or something. So I'm going to give you just so Nishant, you are laughing.
We are talking about outside that today we will get some assignment.
You should have asked me. Okay. You are happy to get assignment. I can give you every day if you want. So, what I'm asking you to do, so in filter, you have to design. Let's give everyone a third order filter. Design a third order filter whose bandwidth is within, let's make, rather than third order, let's make it second order. Third will be better actually, because third order within one is with 10 hertz to 100 hertz. Design a third order filter with bandwidth of 3 kilohertz to how much? 3 kilo to 22 kilohertz. Design a second order filter with bandwidth fourth. So how many students are there? 1, 2, 3, 4, 5, 6, 7. Okay. So this is for specifically for Raman. Pratik is here. Huh? Where he went? But he came and then went. Okay. Okay. I hope he is still with us, right? Okay. So Raman will do this. For this one, who wants to volunteer? Or let's design a second order filter with bandwidth of 100 kilo to 1 gigahertz, or let's make 1 mega to 100 megahertz, right? So who wants to do this? Maybe you want to do this, right? So Shashwat, right? Okay. So third order filter whose bandwidth is within 10 hertz to 100 hertz. Who wants to do this? This third order, let's do it to Nazrul. What about this one? Okay, this is third order. So instead of this is correct spelling, by the way. Okay. So 3 kilo, 22 kilo. Who wants to do this? Nishant, right? Fifth, let's say 1 kilo to 100 kilo hertz. Second order, Siddhant. Right? Maybe 1 mega to 100 mega. Third, Saurabh. Okay, now let's add something here. So this is third order, Butterworth approximation, Chebyshev approximation, Butterworth, Chebyshev, Butterworth, Chebyshev, Butterworth. Okay. You left. Okay, sorry, I forgot. So, do you want seventh order, eighth order? Which order? Okay. Sandeep, I already gave Saurabh third. So, you will be third order. Okay. 1 kilo to 100 kilo. Butterworth. Right? Yeah. Now, happy? So those who are doing their MTech project with me, I gave third order. One who is doing PhD, I gave third order. Nishant is already like A. He got A in analog, so he has to be given third order, right? Okay. So is it doable, right? You have to work little bit hard. Subham is second is fine, right? Yeah. If you want, I can add 2-3 order more. Anyway, so the main thing is you need to look at the frequency, and accordingly you have to design whether switch cap filter or GMC filter. You have to think wisely which needs to be taken into account, right? And then if you are taking GMC, so then you have to design GM. If you are designing switch cap, you have to design op amp with all these switches, right? So that is the thing. So for designing such thing, there are many ways to design. This is how you will go through this Butterworth and Chebyshev. At least what are the approximation, right? If you want to see those approximation, those are given in like the first book of Behzad Razavi, Microelectronics Fundamentals. So it is also given there. Then just you have to replace RC with switch cap, or if you are in GMC, you have to replace, or you have to use that entire transfer function, and you have to make the block diagram, right? Through block diagram you can make GMC. What do you say? Right? It's doable, right? You are already working on this, so there is no problem. Okay, and I gave what you are doing. I'm not giving something new. So this is for 10 days, right? Please note the deadline, right, for them. So after 10 days, what will be there after 10 days? So April 20. Okay, so this is the deadline which you need to actually take care, right? So here we studied so many GM implementation. So you can use any GM technique if you want to use it, which has to be linear, right? When I'm saying linear, it has good SNR. By the way, by chance, do you know what is IIP3, IIP2, all these things? You heard about this? You heard about this or no? You studied communication or okay? Saurabh, you studied where? Hmm? Okay. What about Siddhant? Do you know about IIP2? Nazrul must have. You are IIP 2, 3 or IIPN. Your BTech is in communication. Others does not have BTech in communication. That's why this communication. Okay, right? It's in communication, right? Dinesh, right? You studied in BTech, right? Communication. Which course? Yeah, communication engineering. They're dealing with this cross modulation. Do you, ISI? You haven't heard about all this, Nazrul? ISI. You have to remember you are communication engineer, right? At the end, so anyway, so let's assume that FFT they were able to do that FFT. No, no, not about trying. So I'm assuming that you did it and then I'm go ahead. You got it. How did you get it?
After giving the stroke period,
Mm-hmm.
because the stroke period was not getting the.
I hope you have not got like these things from Suhel.
No.
Okay, you did it on your own or?
No, paper was from IIC Academies.
Mm-hmm.
Tutorial.
Okay.
Stroke period was not getting the multiple of the sampling frequency.
Okay. So if there is Vn which is on log scale, you might have something like minus 100 dB or something, right? Starting from minus 100 to you go till maybe 0 dB or maybe higher than that. This is on log scale, by the way. This is on log, written in dB. Here this side is V out, it's in decibel. So what do you think if there is okay, first of all you understand all the signals are having following things. All the signals which are non-linear by nature, they are going to have fundamental, second, third, and so on, right? All the harmonics will be there. Output as a function of this, right? So fundamental is the one which I am talking about right now. If I am plotting V out as a function of fundamental, right? Or you can say that it will be A sine omega t, where A is actually the amplitude of fundamental. So what do you think the slope of, so if I draw this, what will be the slope? Yeah, so A, right, basically. But other word, if I am increasing this, let's assume that you are here, right? If this is somewhere minus 80 dB and there is something called octave. Octave is how much?
60.
So minus 74 dB. If you are going by octave, how much difference you are going to observe here? Okay, let's go this way. V out is equal to some V in times A. Plot it. If I increase V in by 2, V out is also increased by 2 with the factor of 2. 2 in factor, it's 6 dB. So I can write down this slope as 6 dB per octave, right? But if I want same thing in here for a decade, it's equivalent to how much? 20 dB per decade, right? Or I made some mistake? No, right? Let's talk in only in octave, right? So it will be 6 dB per octave. But other way around, if I am drawing not fundamental, but if I am drawing second harmonic, second harmonic is the one when it's sine 2 omega t times A, but this A will be, let's call this one A2. So which tells you that A1 is higher or A2 is higher? A1 is greater than A2. And can you tell me what is going to happen here? Do you remember the Taylor series? Through Taylor series, can you write down in your notebook and just tell me? So wherever there is a d square, right? So wherever there is a x square term will be there, which is going to contribute to omega t. Actually, you will see that this is a square, right? So, and at that time, this a1 and this will be same. I don't have that slide, but we derived it once where this was coming a square. So, what do you think about this one? If it is square, if I am taking the log, it becomes 12 dB per octave. For third one, it's a cube, which is becoming 18 dB per octave, right? So here there is a one thing, this is going to happen. Right? And other things can be drawn. So here, what are we getting as an information? Have you ever seen this such kind of plot, Raman? Saurabh, have you seen such kind of plot ever? Okay. No, then this is the most important plot. If in communication, it is there. So generally, RF people, they use it every day. Even for those who are working in like ADC or high speed things, they are dealing with this. What it tells you, whenever this touches and this side it touches somewhere. By the way, remember this is just an approximation. Right now this plot is not the actual one. The actual plot will look like this one. Why is it happening so? What do you think? Why this is happening? Siddhant, what do you think? Why this plot is deviating from its value? Any guess? Look, every analog system or any system, whichever you are using, the only problem is its non-linearity is saturation, right? So what do you mean by saturation? It will reach the supply voltage. So here, at some point, it will reach there, and it will start saturating. And same thing will happen to second, third, fourth harmonics, right? This is going to happen. But when you want to do some analysis, what you are going to say, because when you are keep on increasing the voltage, let's say you have given fundamental is equal to supply voltage, this is exactly equal to VDD, it reached. What do you think what will happen to second harmonic? It might be near to second VDD only, or third harmonic will be just little bit below, or maybe in the range of VDD only, right? Now if you are keep on increasing input even beyond VDD, still like all will reach VDD someday. So that is what happening here. Maybe all will reach VDD. You can give input, no problem, right? Until you are not damaging your transistor, you can do all these things. Now what information I want? I want some information. If I am doing this thing, but there are some of the circuits where we are applying fundamental, which is little bit lower than VDD, but it goes, the second harmonic and third harmonic goes beyond your fundamental. This might happen. Means your badly designed circuit, right? So I need to find out that point after which second harmonic will be higher than fundamental, or third harmonic will be higher than fundamental. I need to find out that point, because I am not going to work after that point. The point when it goes beyond, like when this guy becomes higher than fundamental, I am going to call that point as IIP2, and I am going to call this one as input intercept point 2. 2 stands for second harmonic. Similarly, the time when the input value where third is becoming higher than fundamental, I am going to call it IIP3. Similarly, I can talk about all IIP2, IIP3, IIP4, IIPN, right? All these are very important. But if this circuit is nearby this, where this difference is very small, maybe you will never observe. You will never observe the cutting point. In reality, you will never observe this cutting point, because all will reach VDD and then settle there. So what approximation we are doing? We are saying that with this 16 dB per octave plot, I am going to make some asymptotic line. 3 lines are there. One is fundamental, one is second, and one is third. I'll make the asymptotic line which are not there, and then I'm going to find out, or I'll extend this point, and that point I'm going to call it IIP2. Similarly, this point I'm going to call it IIP3. Similarly, you may feel that what these points are. So these points are known as OIP2 and OIP3. Maybe you can guess the full form now. It's output intercept point 2 and output intercept point 3, right? These are the limiting factor for any high speed circuits. Sometimes maybe like if this point is, if I'm telling you that if you are working at 3.3 volt and your IIP2 and IIP3, this is 0 dB, and if this is minus 6 dB, what do you think? Is it a good circuit or a bad circuit? Now you understand what is IIP2 and IIP3, right? So what do you think? Is it a good circuit or a bad circuit? What is 0 dB, by the way, in volts? 1 volt, right? Yeah. So your point is correct. ICMR is less, right? So you're working at 3.3 volt, but your circuit starts saturating at 1 volt itself. There is no swing, right? So in other way around, you can say that this is not a good circuit. If it is like IIP2 is 2 volt and others are, it depends on your requirement also. So these are the requirements you need to derive for your circuit. If it is GMC filter, if it is low noise instrumentation amplifier, for all the circuits which are going to be worked at very high frequency, then you need to look at all these things. These things matter at high frequency generally. This does not happen at very low frequency because these harmonics and other things are playing a role actually, right? So now you know about this plot. So what will be the slope for fifth harmonic, by the way? 30 dB per octave. You should not miss the unit, which is dB per octave, right? So any doubt in this one? Look at these. These plots are actually working when input is in log scale. Both sides it's actually I should write dBV because it's not a ratio, but it's just output and input. Yeah.
So then you told that it's not getting the full speed at
Yeah.
high frequency.
So if you are designing badly, then such problems you will experience at high frequency rather than at low frequency.
So is there any remedy for that? Design in a better way.
So the thing is, if you are working at 50 hertz, let's say fundamental 50 hertz, second harmonic is at 100 hertz, so it takes more time to have the second harmonic. But if you are at 1 gigahertz, every 1 nanosecond you are seeing second harmonic or third harmonic, right? So this has more chances to get poor performance in terms of IIP2, IIP3, right? So such things are there. So sometimes we are going to use these as your specifications, right? Anyway, so yeah, I thought a lot and then I thought we should not, there is no need to discuss this circuit. But one thing is there, when you are designing a circuit which is GMC filter, so it's difficult to get the value which you want cross corner. Like your GM is actually open loop. At some corner you are getting very good GM, some corners you are getting very poor gain, right? So that's not a good, okay, where it went. So what I meant to say, let's assume that you are designing a simple circuit like this. If you are designing this and if this is and op amp, the gain is moving around the corner, right? All corner. But you made some budget and you kept it here with the budget. That for all corners, slow, slow, fast, all five corners with temperature, with voltage, you checked everything. And you told that, okay, this is giving you what you wanted at the worst corner. And other corners, it's good. Now, the next thing is when you are keeping R and C on chip, how much guarantee is there this R and C value will be same? You wanted to design it for, let's say, 100 kilohertz, but for worst case corner, this is 100 kilo. For the best case corner, it's 10 megahertz. Such thing you are going to observe, and if this frequency is increasing, believe me, it will consume more power, right? So operation has increased with the frequency. So what are you going to do in that case? We can make these resistances or capacitors tunable. If look, one of the thing which is tunable, which is going to give me like this equation 1 by 2 pi RC. Let's see be changing on the basis of value of C. I am going to change value of resistance. I can do that, right? So if I am doing this, then I can tune it for a given corner, or for any value I can do that. But the most important part is how to make this potentiometer. How to tune it? What do you think? Huh? Okay, so what you are saying, so he is designing, let's say, fully differential filter like this. So what he is saying, instead of this, let's add something. This is what you are suggesting, right? Where there is a controlling voltage across corners, across different places, it has to be different. But this control voltage has to be controlled by two things. You need to look at the output, right? And from here you need to find out what frequency you are getting. If you are not getting that frequency, then you need to make something reference, and then you need to change this voltage accordingly. So there is some hidden thing is also there, that you are making some compensation technique through which this frequency will be compensated. And this controlling voltage across different corners, you will have different voltages, right? So this is what we can do it in general, right? There is a good paper which is actually, because of less amount of time, it's not possible to discuss this thing. But what is the name of this paper? So this is very popular paper which was in TCAS. It's February 1986. Some of you didn't even took birth, right, at that time. So it's CVDs, Mihai Banu and John Corey. It's a good paper. If you like there is one more paper by same Yanni CVDs, Strange Ways to Use MOSFET. By Yanni CVDs at ISCAS 99. Yeah, correct, right? This is 99. You read this, right? Saw the paper, but you didn't know that it's ISCAS. So, okay, Dinesh has also one paper. Two papers in ISCAS. One, Vijender also has one paper in ISCAS. Our group is also doing some reputed work, right? Okay. So anyway, you can read about this. If we have time, I'll discuss about this maybe in future. But we need to go to the real thing, which is actually the converters, right?
So if I design a graph,
Mm-hmm.
I check the gain at typical column. Then I vary the process column.
Hmm.
And gain varies.
Hmm.
So how would I know that which parameter is varying according to gain varies?
Okay.
It is in my hand to control the process column.
Yeah, sometimes it's in your hand. Look, the suggestion is as follows. Uh, let's say sometimes what is happening, you are tuning W by parametric analysis. If you are tuning it, what is happening? Sometimes you are getting something like this. This may happen, right? If you are doing this, and if you are giving this value of W, at this value this is working. If you remove the last one, and if it is not working, means this particular transistor is actually very much sensitive to the process corner, and you should not do that. Generally my suggestion is, if you are working in nanometer, so your changes has to be in nanometer only. So nano is happening till here. So you should change something here only till 2 or 3 decimals, not more than that. If you are going beyond that, means it's wrong, because minimum is 130 nanometer. Let's assume that you are working in 130 nanometer. You should not make the delta change lesser than 130 nanometer. If it is lesser than that, it's process sensitive thing. Lesser than 130 nanometer. Let's assume that I am making some, like at the bigger side I can make. So I'm not talking about the small thing like 131 nanometer and something. These are the small thing. But if here something in micrometer, then you should not look at something which is 130 nanometer. If you are doing changes by more than lesser than 130 nanometer, it will be not sensitive, right? That is what I'm saying. And these are with the observations. These are not written in any book. This is with observation. As you are saying, sometimes what people are doing, they are tuning the wrong transistors. They are tuning the wrong transistors. Let's assume that you are designing such circuit. Now what is the gain, by the way? So what is the gain? GM, let's assume this is M1, this is M0, this is V bias, right? So GM times some RO, right? Because this current is having infinite resistance. Yes, Nissan, so it's GM times RO, right? So what do you need to touch in reality? One day I found out, I did not give you the name of the one who was doing this last year. So in analog, those group of people were tuning this, and somehow they were changing the gain without understanding. It's wrong, right? You can understand this. If you need to increase the gain, you need to touch these two, only these two. When you are touching this, you are touching for following things. You are also touching input referred noise, right? You are touching UGBW, not bandwidth, because bandwidth is controlled here. If you want to touch UGBW, through which gain is controlled, so ultimately you are touching gain, right? If you want to change, let's say bandwidth, use try to use or try to tune M0, nothing else, right? So if you are doing something which is sometimes not relevant, Some people are changing L like so much. Then there are lots of things are happening here and there. For let's say if I am increasing GM times RO, by increasing L I can increase RO, no problem, right? But some reverse effect will come to GM also. Sometimes some people are working at 28 nanometer but gives the L of something like 10 micrometer. I've seen it, those people, right, Dinesh? We experience. So they know who has done all this thing, and everybody were following that particular group. So you have to do the things systematically. You have to follow the equations. You have to try to, like, I know that current mirror I need bigger L. I can understand this. But if I'm doing or changing RO abruptly here by changing L, actually you are touching GM also. By changing L here, you are not only touching RO, you are touching GM, right? So there are many other effects which is coming into picture without giving any invitation, right? So when you are designing the things systematically, you will see minimum variation, right? Like in difference amplifier, what Pratik has designed, having minimum variation. For your case, as circuit is becoming bigger, unknowingly you are touching some unwanted things, right? And that's how, like, at one corner he was getting 120 dB. That's a typical corner. At slow corner he was getting minus 40 dB. Sorry, minus 40, minus 14 dB. Okay. So one corner was 14 dB and one corner was minus 3 dB. So tell me, he has designed his op amp at 120 dB, but in reality one corner is 14 dB, one corner minus 3 dB, some of the corners 98, and all these things are happening. So this suggests that some of the transistors are out of saturation, first of all, right? To make them in saturation means your common mode has been actually it's varying. So when it's varying, you need to make sure that common mode has to be tuned through a common mode feedback circuitry. That is what he has done. When he has done this, things were fine. But one more important thing, if you are designing an op amp, remember it's not a comparator, it's a it's an op amp. If you are designing an op amp, you have to make sure that output uh, is with respect to what you want, like whatever is plus, that will go to minus, right? V plus equal to V minus. I'm neglecting input offset voltage and other things, right? There must be some input offset voltage plus or minus, but still you are going to get some connection, right? So V plus equal to V minus. If you are doing this open loop, so most of the people, they are doing open loop like this, right? If you are doing this, this is not the simulation of operational amplifier. This is the simulation of comparator, which is comparing two things, and other things are independent. Look, if I'm doing this for a circuit which looks like this one, right? So it's sensitive to process for sure. Gain is sensitive to process because your common mode is not the one which you expect. So what do you think? What will be the output here? I should say common mode voltage, not gain. Here, let's assume that I'm 1.8. By the way, are you following what is going on? Everybody, right? This is 1.8. I'm giving, let's assume that it's 0.9 volt both sides. What will be voltage over here? It may not be 0.9. You will never get 0.9. If it is 0.9, like these two are short circuit, then and then this will happen, right? So you have to have something higher than 0.9 here. If you want to find out, it's by VTH, right? In terms of VTH, you can write down those things. We did it right in your analog course. So it will be, let's assume that it's 1.2 volt. If it is 1.2 volt, then I need to give it to here, not there, right? I just made it, right? So if it is 1.2 volt here, what will be the voltage over here? Hmm? Greater than 1 by 1.2. Will it work? This is fine, everything is fine. So if this is 1.2, this will be 0.6 volt, right? So all the drop is here, not here. Sometimes you will see the situation that this is not 0.6, it's just 0.2 volt and 1.6 volt is here, right? But do you need this one? Is it correct? Why you don't need it? No, you are missing something. Everything is, let's assume that okay, you don't like this, then let's make this one 0.3 volt. It's in saturation. Yeah, what do you output swing is limited, but sometimes that is the correct answer. Sometimes that's the correct answer. How do you know that this is the correct answer or not? That's why I told you there are two kinds of simulation. One is operational amplifier op amp and one is called comparator. Right now what you are doing is comparator. Look at this. This is open loop. Everything is going in open loop. None of the op amp will be in open loop. It will be always in feedback, preferably in negative feedback, right? If it is in negative feedback and if you want to declare that one as negative feedback, let's assume that this is the case, right? So on the basis of what V1, which is composed of DC and AC both, you are going to get forcefully some DC potential here itself. So what does it mean? This is the circuit. So it's in feedback. On the basis of what DC potential you are giving here, inside it's infinite. So it will not go here, but it will go here for sure. Whatever 1.6 volt or it doesn't matter. It's coming from independent source. So the lower resistance path will take care, and you will not have 1.6 volt. You will have something else, right? If you remember, the worst case condition is the one when there is unity gain feedback. The worst case condition occurs when your system is in feedback. Open loop looks like this one. When you are making in feedback, if you remember, it was going like this. And in negative feedback, when this unity gain, there was one bump over here and coming there, right? So the worst case condition, that's the unity gain. So you need to check everything at unity gain. If I want to make it unity gain, what I can do, I'm going to add one inductor over here, and note that this is just for a simulation. Okay, not here. Right? If I'm keeping this inductor, what does it mean? At low frequency, there is a short circuit. Low frequency is a common mode voltage where whatever the common mode voltage I am giving here, that will directly go here. If it is 0.9, that will be 0.9. For a given 0.9 volt, I am going to have the maximum swing. But what you are doing, open loop, it was not maximum. Accordingly, if it is 0.9 volt, other things will change. Right? It might be sometimes I am not going to keep it 0.9, but I am going to give 1 volt, 1.1 volt. Depends. It's not exactly half. It depends on what common mode, I am going to get it from the previous stage. And what configuration I am designing, I'm designing something else also. So preferably when it's negative feedback, the worst case is happening at unity gain. That's why we are keeping two inductors also in feedback for a simulation. Right? We discussed this in the laboratory, right? In E512. So sometimes this is what we want, and sometimes what we want, we don't want the interaction from. Look, once I'm keeping here 1.1 volt. I don't want this 1.1 volt to be changed. So I keep some big capacitor also, which will not allow this 1.1 volt to go that side. Right? So this is simulation technique. In reality, we are not going to add inductor and capacitor when you have 741 IC or other things. Then you are going to do the simulation normally. If you are keeping op-amp in open loop, it's actually comparator. If you are keeping with some resistances, it's in like feedback, negative feedback. So if you look at the 741 IC's data sheet, they are showing when it's both the resistances are equal, what is happening, through which they are finding out the unity gain bandwidth. Then they are keep on tuning this resistance and looking at what is the gain. Right? So this is how it goes. Right? So you need to simulate it using inductors and capacitors. If you are not doing that, maybe your answer will change. I hope you are doing that. If no, I'm telling you every time and you are making same mistake, then I don't know. You need to add something like 1 Henry. Okay, it's a big inductor, but we are not going to tap it out ever. This is just for simulation technique through which you are making short at the low frequency. That low frequency is right. So if you take something else, then the answer will be different. Right? So this is how it goes, and that is how I explain you that whenever there is an op-amp which is not kept in feedback, then you don't worry about common mode feedback. Right? It's an open loop. But if it is in feedback, and if you are going to connect in single stage, you don't need common mode feedback. If you have two stage, you need common mode feedback. For odd number of stages, CMFB is not required. For even number of stages, CMFB is required. So this is the reality. Because in between the stage, you don't know what is happening. So for such case, even if it is like common mode feedback will be needed for sure, because it's two stage. For the case of one only odd stage, are you following what I mean? So if let's assume that this is an inverter, right? This circuit was also an inverter whose gain is very high, whose gain is minus GMRO. So it's an inverter. Whatever you are giving as input, output will be actually inverted version of that. So I'm calling it inverter, right? Depending on what kind of inverter, class A, class B, it's depending on the efficiency. So we are not looking into that. But if such system is like this, whose gain is if it is if there are two resistances which are going to give you negative feedback, and the answer is, let's say, V in by V out. So it has to be same, right? Or A by 1 plus A beta, where A is 10 and you have to find out resistance. In feedback we did it. So if there are stages are more, if one stage is there, I can draw something called, so if there is input and if there is an output, if you are moving from So this is open loop thing I am drawing. So open loop differential gain will look like this one. Do you agree with me? With the saturation, this will be VDD, this will be VSS, and there is a slope. There is no offset. Let's say this is small signal AC gain, which is inverted one. But if you are looking at the common mode gain will be in first quadrant and third quadrant. The reason is gain is in positive. The common mode gain is positive. Then small signal gain is negative, right? AC gain is negative. So there is only one point where they are going to meet if I am going to keep them in feedback. That midpoint will be exactly midpoint. You're following this, right? But if there are, so this is true for all the odd number of stages. So there is only one stable point, which is VDD plus VDD minus VSS divided by 2, right? But if you have even number of stages, you may have more number of stable points. When I'm saying stable points, these are the values where your output will sit. At the output, you may have VDD, you may have VSS, you may have like 0.9 also. At typical corner, you can see 0.9 and you will be happy. But in reality, across the thing, you can have different process corner and your common mode will be sitting somewhere else. This is happening because of the reason that, let's say, assuming the even number of stages, so who is controlling this point? Nobody, right? But if it is one stage, if I am keeping the feedback, the input itself is actually taking care of this output. And same thing is happening for all odd number of stages, because there is only one stable point always, right? So it's like this kind of situation. If I am starting the ball from here or from here, it will reach here only. So this is called a stable system, right? Because only one stable point. But if you are here, you can go this side also and you can go this side also. If there are different stable point, so that's a metastability condition. And if it's a metastable, you need CMFP to fix your process corner variations. Right. So just for op-amp, I'm explaining you what needs to be done. Yeah, for all BJT MOSFET, this is for true for actually for this is true for all op-amp circuits. Whatever you studied in your E512, this is true for that. But this is not true for GMC filter. GMC filter, when I wanted to make this one, let's assume that this is op-amp plus CMFP, who is actually designed very good way, and it gives all the results. But through this circuit, what do you want? You want bandwidth of 1 by 2 pi RC, right? If you want this, what is the thing which is causing a problem to you? Not the gain of op-amp. It has been checked. Op-amp is fine, no problem. I checked it. So the problem is either resistance or capacitance. Maybe at one corner you are seeing 1 kilo, one corner you are seeing 1 mega. So resistance is either decreasing or increasing, or capacitance is increasing, decreasing, because there are two more corners. One is called R tip, one is called R min, one is called R max corner. Similarly, C tip, C min corner, and C max corner. So on top of 125 corners, the corners will be increasing. So these values are also increasing or decreasing with the value of capacitances, value of temperature. These things will be changing. So what I can do, I can fix one value. Let's assume that I'm fixing the value of capacitance. Let it be changing. And I'm going to change resistance. To change this resistance, what I'm going to see, V out, what is the frequency? That frequency will be compared with the reference frequency which I need, and that going to be changing the voltage here, and that is what I was explaining you, that is happening at cross corner, right? If the variation is very high, then you cannot make the budget like this. Then you need to make some circuit called master circuit, which is tuning all the slaves. This kind of circuit is called master and slave. Actually, that is what I kept it, but you asked me the question, which is is there or not? You need to tune it. If it is largely varying, if it is not largely varying, and then you can make the budget. What's the problem, right? If power budget is not a problem, then you can bypass this master slave approach. Otherwise, you need to keep that. All the filter circuits, all the resistances has to be tuned in reality. That's how, like, filter is one of the difficult topic. Some of the people are working in filter from like last 30-35 years of their whole life. They are working only in filter. They don't work on anything else. It's a big thing. All the circuits need filter. All circuits, either analog or digital, right? Yeah. Does it answer your question, or okay? This was helpful for others also, I believe. I thought it will be difficult topic, so I didn't discuss that. I was bypassing, but when he asked the question, I thought, okay, still people are with me, so I explained that also, right? Hmm.
Frequency one is one at one corner is 1 kilo and another corner is 10K. Then tuning is required.
It's depending on power consumption. So your power consumption is within the range. Even from 1 kilo to 1 mega, that is also allowed. I'm allowing people, those who are working with me, if I have power as limit. If you're when you're designing master slave, so master, let's assume that it's consuming 100 microampere, and the slave is consuming something, let's say 200 microampere, so it becomes 300 microampere, right? And in this case, 1k to 1 mega, with this variation, if it is 500 microampere, but still the one who has given you the specifications, he allows 500 microampere, then you should not go for master slave. It's all about other requirements, and it's trade-off, because when you are doing this, its area will increase for sure, right? You have to save area also, right? Does it answer your question, or still confusion? Nishant, you want to ask anything?
Sir, in our case, in our design, so how much budget?
So I'm telling you that, and design it without master slave, right? Design without master slave. As much power you are burning, let's burn that power. But GM is in feedback. GM is in feedback, so make sure that You are designing everything with inductor. Everything has to be designed with inductor, and then you need to remove this. This is just for simulation. With inductor, whatever the results you are getting, that needs to be quoted, not the one without inductor, because what you are seeing, it's comparator results, right? It's op-amp as a comparator, right? I think this clears your doubt also. So sometimes if you're keeping in inductor in negative feedback, maybe at all corners it will work, because this common mode voltage will not change here and there. Earlier time it was moving here and there. There are two different things. If you look at what this circuit is, so here it's fixed. This point and this points both are fixed, right? When you are keeping an inductor. Similarly here and here, as we were getting 1.2 volt, the results will be different with the different common mode value, right? So this is Vi plus VCM, this is minus Vi plus VCM, right? Right now if I am doing the simulation, I'll get maybe for a VCM of 0.9 volt, maybe 1.2 volt, right? VTH will be added. But when I'm not doing this, but I'm doing this, means plus and minus. So this is plus, this is minus, has to be right. So it's a negative feedback. When you're doing this, you're forcefully connecting this to 0.9 volt. Look at this. You're shorting them at DC potential, right? Not all other frequency. When you are moving away from zero frequency, this will be open circuit. Right? Unfortunately, this is not given in any book. But this is the thing. Maybe like right now, some of the people will think that whether other people are using or not, but all industry people are simulating op amps using inductors and capacitors only, right? So you have to follow that only.
So we'll use capacitor in case of high frequency.
Every time. If you are using inductor, you have to use capacitor also. But without capacitor, you can do it. It's not a problem. With capacitor, you will make sure that both side inputs are V plus equal to V minus. Right? Is it given in Willis Hanson? Or, right? I didn't find any book where it is given. I haven't gone through Shanti Pawan's lecture, but whether he is talking about this. Okay. Anybody who, right? But yeah, if you are going from Shauri Chatterjee's video lectures, he is talking about this. He is from IIT Delhi. I have all of them. I recorded them. I was his dear. So he is my PhD supervisor. So I can give you all the video lectures. In my opinion, he is the best teacher. So if you want, I can give you those lectures. Must be somewhere he's talking about inductor, if I remember correctly. Right. Just give me your pen drive, I'll give you. All the lectures must be in my laptop. I gave it to you, right? Okay. Because I gave all the lectures. I have. Okay, in my hard drive, not. Okay. I thought I gave it to you, your hard drive. So if you want all the lectures, I'll give you. From Datta Roy, even all big shots. You should listen to them. It's available also on NPTEL. You should go to web.iitd.ac.in with tilde sorry, and then you have to go to E789, which is CMOS analog IC design course, where all the lectures are available in the form of SWF. If he has removed it, then you can talk to me, I'll give you.